Induction motors are the most commonly used electrical machines. They are cheaper, rugged, and easier to maintain compared to other alternatives. In this video, we will learn the working of a three-phase squirrel cage induction motor. It has two main parts, stator and rotor. Stator is a stationary part, and rotor is the rotating part. Stator is made by stacking thin-slotted, highly permeable steel laminations inside a steel or cast iron frame. Winding passes through slots of stator. When a three-phase AC current passes through it, something very interesting happens. It produces a rotating magnetic field. To understand this phenomenon much better, consider a simplified three-phase winding with just 3 coils. A wire carrying current produces magnetic field around it. Now, for this special arrangement, magnetic field produced by three-phase AC current will be as shown at a particular instant. With variation in AC current, magnetic field takes a different orientation as shown. From these 3 positions, it's clear that it's like a magnetic field of uniform strength rotating. The speed of rotation of a magnetic field is known as synchronous speed. Assume you're putting a closed conductor inside it. Since the magnetic field is fluctuating, an EMF will be induced in the loop according to Faraday's law. The EMF will produce a current through the loop. So, the situation has become like a current-carrying loop is situated in a magnetic field. This will produce magnetic force in loop, according to Lorentz law. So, the loop will start rotating. A similar phenomenon happens inside an induction motor also. Here, instead of a simple loop, something very similar to a squirrel cage is used. Three-phase AC current passing through stator winding produces a rotating magnetic field. So, as in the previous case, current will be induced in bars of squirrel cage, which is shortened by end rings, and will start rotating. That's why it's called an induction motor. Electricity is inducted in the rotor by magnetic induction rather than direct electric connection. To aid such electromagnetic induction, insulated iron core lamina are packed inside the rotor. Such small slices of iron make sure that eddy current losses are minimum. This is another big advantage of a three-phase induction motor. It is inherently self-starting. So, you can see here that both magnetic field and rotor are rotating. But at what speed will the rotor rotate? To obtain this answer, let's consider different cases. Consider a case where the rotor speed is the same as the magnetic field speed. Since both are rotating at the same speed, the rotating loop will always experience constant magnetic field. So, there won't be any induced EMF and current. This means zero force on rotor bars. So, the rotors will gradually slow down. But as it slows down, rotor loops will experience a varying magnetic field. So, induced current and force will rise again. And the rotor will speed up. In short, the rotor will never be able to catch up with the speed of the magnetic field. It rotates at a specific speed, which is slightly less than synchronous speed. The difference between synchronous and rotor speed is known as slip. Rotational mechanical power is transferred through a power shaft. In short, in an induction motor, electrical energy is entered via stator and output from motor. Mechanical rotation is received from rotor. Energy loss during motor operation is dissipated as heat. So, a fan at the other end helps in cooling down the motor. Hope you got a good introduction on the working of induction motors. Thank you.
As the name suggests, synchronous motors are capable of running at constant speed irrespective of the load acting on them. They are machines with high efficiency and are mainly used in high-precision applications. The constant speed characteristic is achieved by interaction between a constant and rotating magnetic field. Rotor of synchronous motor produces constant magnetic field, and stator produces revolving magnetic field. The field coil of stator is excited by a three-phase AC supply. This will produce a revolving magnetic field, which rotates at synchronous speed. Rotor is excited by a DC power supply, so it acts like a permanent magnet. Alternatively, rotor can also be made of permanent magnet. Interaction of rotor and RMF is interesting. Assume you are giving an initial rotation to the rotor with same direction of RMF. You can see that opposite poles of RMF and rotor will attract each other, and they will get locked magnetically. This means that rotor will rotate the same speed of RMF, or rotor will rotate at synchronous speed. Synchronous speed can easily be derived as follows. This means that if one has got control over frequency of the electricity, speed of synchronous motor can be very accurately controlled. But if the rotor has got no initial rotation, situation is quite different. North pole of the rotor will obviously get attracted by south pole of RMF and will start to move in the same direction. But since the rotor has got some inertia, this starting speed will be very low. By this time, south pole of RMF will be replaced by a north pole, so it will give repulsive force. As a net effect, rotor won't be able to start, or synchronous motors are not inherently self-starting. To make synchronous motor self-start, a squirrel cage arrangement is cleverly fitted through pole tips. At the starting, rotor field coils are not energized, so with revolving magnetic field, electricity is induced in squirrel cage bars, and rotor starts rotating just like an induction motor. When the rotor has achieved its maximum speed, rotor field coils are energized. So as discussed earlier, poles of rotor gets locked with poles of RMF and will start rotating at synchronous speed. When rotor rotates at synchronous speed, relative motion between squirrel cage and RMF is zero. This means zero current and force on squirrel cage bars. Thus, it will not affect synchronized operation of motor. Synchronous motors will produce constant speed irrespective of motor load only if the load is within the capability of motor. If external torque load is more than torque produced by the motor, it will slip out of synchronism and will come to rest. Low supply voltage and excitation voltage are other reasons of going out of synchronism. It is interesting to note that synchronous motor has got the same constructional features of an alternator. Synchronous motors also helps in improving overall power factor of the system. That's all about working of synchronous motors. Thank you.